You've done as much as you can to reduce noise in your AFM and to make good AFM images. But there are situations in which you have an image that's imperfect or a little bit messy, and you need to clean it up because you're under time pressure. You might have to finish a report, your boss might be leaving for a meeting and needs a slide, and so forth and so on. There are all sorts of image processing options, and most of them are fairly easy to understand. The one thing that I've been finding that it's hard to convey is Fourier filtering. And as the name implies, we're going to be using Fourier transforms for this. So there are two types of Fourier filtering I'm going to tell you about. One is threshold filtering, and the other is frequency filtering. And it's the same idea as we saw in noise analysis. You transform from the time domain to the frequency domain, and in the frequency domain you can see things going on more easily than you can in the time domain. Now, images are not presented as a time. They're presented as a function of position. And just as time and frequency are inverses of each other, position has an inverse, which in physics is called k-space. But let's avoid that terminology and just say we have position. Call it r in the general sense of including both x and y. And the inverse of that, we'll just call it 1 over r, not to add any more variables to our discussion. So before I tell you about the filtering, I just want to make sure that you're comfortable with a very important idea in Fourier analysis, and that is any periodic function can be represented by a sum of an average value and sine and cosine waves of different amplitudes and frequencies. You can also show that this applies to any function in general. Let's do that first. Here we have half a cycle of a triangle wave. Voltage is a function of time. If we want to represent that as a sum of sine and cosine waves, what would we do? Well, first of all, it wouldn't be cosine. Cosine starts off as 1 at time equals 0, and so that is out of phase with this triangle wave, and so we would be using a sine wave, which is in phase with this triangle wave. And so our first attempt would be the same frequency as a triangle wave, looking something like that. That's a half cycle of a sine wave. But you see, the sine wave is fatter on the sides and not as tall as the triangle wave. So what would we try next? Well, we might try something with twice the frequency. And if we were to add that yellow line to the blue line, that's not going to help either. It would make the triangle wave fatter on one side. It would be kind of lopsided where the triangle wave is going like that. So let us try another frequency. Let's go up one. Let's go up to 3 times the frequency. So that's promising because when we add that rose line to the blue line, and we would get a little decrease here on the sides and a little increase here near the peak. So we start to get something that more closely resembles the triangle wave. And it turns out we keep on doing that, and it's only odd multiples of that original frequency. So do what's called the fundamental, and then 3 times, 5 times, 7 times, and so forth. Those multiples are called harmonics, and when you have only the odd ones, you would have the odd harmonics. So if I were to draw the Fourier transform of a triangle wave, I'm going to draw it in the middle here. So now frequency, voltage, and the blue would be the fundamental at a strong frequency, and the rose would be 3 times that at a lower frequency, and then higher, the next one would be number 5 up here. Turns out it's at a lower frequency. Still, and that goes out in frequency. So what we're going to do is the following process. There is a 4-step process. No matter which kind of Fourier filtering you're doing, you have your image, you do the Fourier transform, and now, because we're talking about more than one direction, the data are presented in terms of a 2-dimensional plane with 1 over x on one axis and 1 over y on the other axis, and the contributions of those frequencies are denoted by colors. The brighter the color, the more amplitude, and then you apply whatever filter you choose to use. You get a modified Fourier transform, and then you do the inverse Fourier transform to get your processed image. It looks like this. Here is, on the left, is our starting image. And you see here, there's some streaks in it. This is a delta function grading that you can use to calibrate your tip, check your calibration of your scanner, etc. And there are situations where you will want the viewer of your image to focus on what's important about it instead of distracting streaks. The sample is particularly difficult to image because of the sudden changes in height. So we want to get rid of these streaks. We do the Fourier transform. The second image, this direction is the 1 over x. This direction is the 1 over y. Now the colors here represent the peaks. And so if you look closely, you'll see little dots here. These are frequencies, inverse distances at which the signal is strong. But I want to get rid of the streaks. I want to keep only the information I want. And so I apply a threshold. And I'm going to keep and retransform only those signals in green here. Okay? And maybe now it's easier to see that there are spots here corresponding to frequencies, inverse distances, that are strong and represent the periodicity of the original image. Then we do the inverse Fourier transform, and here we have our filtered image. Now, filtering is a matter of judgment. If you go too far, you will radically distort your original image. And that can be fun to play with, but it's not fair to present your work as being radically different than the original. And here, this is really at the limit of what can be done with threshold filtering, because I can see that the edges here are distorted. Although the streaks are gone, and we can show this image and talk about the periodicity of these features. Now, threshold filtering only works when the signal of interest is greater than the distracting signal, the noise, the streaks. If you raise your threshold too high, higher than the signal of interest, to get rid of noise that might be higher than the signal of interest, well, then you take out the signal of interest too. So threshold image filtering doesn't work for every situation. That's why we need frequency filtering. Frequency filtering now. In the top row we have real space images, i.e. the topography, and in the bottom row we have the two-dimensional Fourier transforms of those. The original is on the left, so the starting image plus its Fourier transform below, and the problem area here is over on the left-hand side. This image was taken in contact mode, and contact mode is subject to friction, such that when an image starts up, the cantilever twists due to friction, and this is called a startup artifact. So for purposes of display, we want to get rid of that startup artifact, and it's a pretty strong signal. Okay. So we've got the original on the left-hand side, and the next in the sequence is a threshold filter. And this threshold filter is pretty strong, and yet still the startup artifact is there. And I say it's pretty strong because you can see some distortion here along these edges. Right? So we don't want to increase the threshold, because then we're going to really distort our original data. So let's try a frequency filter. These two images here, third in the row, the original data were taken, and now we're going to retransform all these sections in green here, leaving out those frequencies that are low and running in the y direction. So low values of inverse x for all amplitudes of inverse y. So that comes out pretty well, as you see. But if you were able to blow this up, as I have on my computer screen, you would still find some sketchy, noisy patterns right in that area. So, of course, what you would naturally want to do, and it is possible, is you do them both. You do both threshold and frequency filtering. And now we end up with very few frequencies in the Fourier transform, just those green dots, where these rectangles here indicate that we want to keep these frequencies, plus we've said we want only those frequencies within those rectangles over a certain threshold to be retransformed. And so this image here is our final image, and it looks quite good.